So this is Engineering Statistics and Linear Algebra 18 EC44. We are in Module 1, Lecture 4, which corresponds to the single random variable expectations, right? So in the expectations, if you see, expectation of a random variable x is generally written as either of the three symbols are used, x bar or e of x or mu of x, okay, is equal to integral minus infinity to plus infinity x fxx dx, where this fxx is the PDF of the random variable x, PDF of the random variable the x. So this is also known as the mean. Sometimes we use the term mean for this, right? So this expansion puts emphasis on what is known as the expectation operator. Okay, we have here e of x. It can be e of anything else. So equation 2.44 is only one example of the use of the expectation operator. In general, we can have the expectation or expected value of any function gx, and that is given as e of gx is equal to integral of minus infinity to infinity gx fxx dx. Again, fxx is the PDF for the random variable capital X. So we are having here three most important expectation operators: ex equal to minus infinity to infinity, x fx x dx. This is what we have considered as the mean, and then e of x square is equal to x square bar equal to integral minus infinity to infinity x square fxx. Then e of x minus mu x whole square is equal to integral minus infinity to infinity x minus mu x square fxx. So this is known as the mean of x, or the first moment of x about the origin. This is known as the mean of the square of x, or the second moment of the x about the origin. So alternative symbol for the e of x square is x square bar. Then the third equation over here is known as the second moment about the mean. So try to differentiate between this. This is second moment about the origin, whereas this is second moment about the mean for the random variable x, or it is also known as, most commonly used term is variance. So variance of x, alternative notation is var x sigma x square is equal to e to the e of x minus mu x square. Okay, so here, if you see here, this is straight away ex is nothing but mu x. Ex is nothing but mu x in the earlier thing over here. Ex and mu x both are same. Okay, so do not get confused there. So here we are using sigma x square. So where sigma x is the standard deviation, right? And it's always positive. And we generally write sigma x as plus of root of variance of x. It cannot be negative. So equations for the sample Sx square are given in the appendix F for different distributions for that. So let us take some examples. So if the expectation in 2.46, 2.47, 2.48, that is all these three equations is to be considered, are applied to the uniform random variable with PDF 2.17. Uniform random variable is constant between y1 and y2. Okay, constant between y1 and y2. Shown in the figure 2.3, we find that mu of y will be equal to y1 to y2, y dy minus y1 minus y2. So uniform distribution will be constant between y1 to y2. Okay, y1 to y2. So that's why you will get this value here. Okay, so the what you call fx value will be this. This is y, or rather this is fy, the what you call PDF of the random variable y for the uniform random variable will be this. Okay, so now if you try to integrate this, this is just a constant, whereas this y is a variable, so you'll get y square by 2. Y square by 2 multiplied by, of course, 1 by y2 minus y1. So if you substitute for y2 and y1 for y, right, you'll get y2 square minus y1 square divided by 2 into y2 minus y1, and you can write the y2 square minus y1 square as y2 plus y1 plus of y2 minus y1 divided by 2 into y2 minus y1. So y2 minus y1, y2 minus y1 will cancel. What remains is y2 plus y1 by 2. Similarly, the expectation of y square will be, here we need to write y square dy divided by y2 minus y1. So now the integral of y square is y cube by 3. Y cube by 3. So you can substitute again the upper limit and lower limit there. So then you'll get y2 cube minus y1 cube divided by 3 into y2 minus y1, and that will give you y2 square plus y2 y1 plus y1 square by 3. This is the value which you will get. Okay. Then the variance which corresponds to sigma y square is equal to integral y1 y2 y minus mu y whole square divided by y2 minus y1. So this you can expand, and if you expand that, you'll get y squared minus 2 mu y plus mu y square. Okay, and then you can simplify that 1 by y2 minus y1. You can take out then each of the terms for which we need to take the integral can be taken. This is just a constant. This is just a constant, so we can take them outside. So this value again is y cube by 3 with limits y2, y1. This is 2 mu y squared by 2 with limits y2 by y1. This is mu y square with the value which is y. Okay, y with limits y2 minus y1. So if you simplify all that, you'll get y2 minus y1 whole square by 12. Next example, if the expectations again same are applied to the normal Gaussian random variable with the PDF given in 2.21, then you'll get the what you call mu z as ez equal to this whole thing. You can just write it over here, 1 by 2 pi integral of minus infinity to infinity z e to the power of minus z squared by 2 dz. So just if you take the PDF, then you'll get 1 by root of 2 pi e to the power z squared by 2. So now this z is multiplied because we are asking for expectation, and then the integration between minus infinity to infinity. Now because this is even term, right? Generally what we have is Ez is a symmetrical, the PDF is a symmetrical curve for Gaussian random variable, and it is symmetrical about x equal to 0 or z equal to 0 or y equal to 0, whatever is the corresponding what you call outcome for the random variable x, y, z. So because of the symmetricity, the what you call odd, generally we call it as odd integrand. Because of the odd integrand, this value will be equal to 0. So again, if you write x e to the e of z cube, that also will be 0. E of z to the power 5 will also be 0. Only ex or rather ez square, that will be z square e z square by 2, z square z to the power 4, all that will have a value because it is even term. So the integral of 2.54 is evaluated directly because the integrand is odd, therefore you'll get 0. The integral for the variance 2.55 as well as the expected value of z square is evaluated by letting dv equal to minus exponential z minus z square by 2 equal to u equal to z, then integrating by parts. So the integrating by parts example is formula is given over here. So we can use that for trying to find the value of these two. This will become 0. This will become 1 if you use this. Okay. So two other expectations of the normalized Gaussian random variable that are sometimes referred to are the coefficient of skew. So ez cube, again this is odd, integrand will become odd, therefore this will be 0. whereas this coefficient of kurtosis e of z to the power 4, and that will become 3, only because of the reason that, this is even, and if it is even, it's a non-zero value, and non-zero value means again you need to do integration by parts. So whether you do this, solve the solution for this and this, you need to use the integration by parts. So evaluating of the integral in 2.56 and 2.7, that is for this is left as an exercise 41-42 in the book. So next is what is known as the linear combination or linear operator. So in linear operator or linear combination of superposition principle, as it is sometimes known as, is generally written like this. Again, in linear algebra also we considered that E of G1x plus G2x equal to E of G1x plus E of G2x. So you can separate them, or you can multiply with a constant that will be like coming out of the function E of C of G of x is equal to C of E of G of x. This observation allows us to use the expectation operator in an algebraic fashion. An example of the linear expectation operator can be seen with transformation like this. However, we can join these two also to get this. Okay, this is generally known as the linear combination, where we write E of C1 Gx plus C2 Fx is equal to C1 E of Gx plus C2 E of Fx. So this is just the combination of these two. So if you take an example, another example of y is equal to ax plus b as the, this is the random variable, that random variable is equal to the ax equal to b, then what will be the expectation or the mean for that will be E of xy equal to E of ax plus b, and that is E of ax plus E of b, and this is just a constant, therefore that will be b itself. Expectation of a constant will be b itself. Expectation of ax will be a, you can take out b of x, that is the multiplication operator which you are using here, and therefore a of bx plus b. Similarly, we can try to find out the variance of the y, which is something like this. Now y minus mu y whole square, so you can expand y, you can write it as ax plus b. Mu y you can write it as a mu x plus b. So b will minus b and minus b will cancel. We are left with ax minus a mu x whole square. So that will turn out to be a, you can take out common, so therefore a squared x minus mu x whole square. And this is just a constant, so again applying the same property, which is the second property there, which corresponds to this, right? You will get it as a squared expectation of x minus mu x whole square, and that is a squared sigma x square. That is the variance of y will be equal to the a square multiplied by the variance of x when y is equal to ax plus b. So we can see that the variance or variability of y depends only on the variance or variability of x, not on the mean of x. So this depends only on the variance of x, but rather it does not depend upon the mean of the y or the x. Okay, the transformation 2.60 and its associated mean 2.61 and the variance 2.62 are quite helpful from time to time as we go forward, that we'll see. So let us take an example here. Suppose we have a random variable x which is uniformly distributed between 0 and 1, then its PDF is written like this, uniformly distributed between 0 and 1. So you can say that it is uniform distribution with y1 equal to 0 and y2 equal to 1. Okay, then we will have the PDF as equal to 1 between 0 to 1 and 0 otherwise. So the expectation obtained from 2.46, 2.47 and 2.48 will be, so these are the three equations, that is expectation of x, expectation of x square, this is the variance. So we are trying to find over here mu x is equal to 0 to 1 x dx equal to 1 by 2. E of x square is equal to integral 0 to 1 x square dx equal to x cubed by 3 with limits 0 and 1, that will give us 1 by 3. Sigma x squared is equal to integral 0 to 1 x minus half whole square dx. So you can expand this, and that is x square minus 2 into half into x plus half square, that is 1 by 4. And you can try to integrate that and solve it, then you get 1 by 12. So the random variable x can be transformed to any other random variable y uniformly distributed between y1 and y2, where y2 is greater than y1. So the desired transformation will become y is equal to y2 minus y1x plus y1. With this you can find. Otherwise you can just compare this with the uniform distribution which you might have considered in the earlier lecture, right? So there, if you just substitute y1 is equal to 0 and y2 equal to 1, then you're going to get all these same values, right? If you just consider the what you call earlier lecture, okay, this is the uniform distribution with the fyy and fxx over here. So you substitute here y1 equal to 0 and y2 equal to 1. Then this will become 1, 0, less than y, less than 1. Okay, that is what this will become. Similarly, if you take their corresponding expectations which we have tried to find in the lecture now, then we can just see that we have got the same thing there in the uniform distribution. Okay, in the example which we have considered in the uniform distribution. So if you just write y1 equal to 0 and y2 equal to 1, we'll get half. Y2 equal to 1 and y1 equal to 0, we'll get 1 by 3. And in the next case here, y1 equal to 0 and y2 equal to 1, we'll get 1 by 12. We'll get 1 by 12 over here. So it's just the same. So this transforms the same as you can just write a equal to y2 minus y1 in whatever we have written there. Okay. So we have written in place of a y2 minus y1 and b as just y1. Okay. And then we will get accordingly the mean will be equal to mu y is equal to y2 minus y1 1 by 2 plus y1, that is y2 plus y1 by 2, and this is what we have got in the uniform distribution. Similarly, the variance of y, you can find out that by using the same method, we'll find that it is equal to this, which we have already got in the 2.5. Yes. This one and the 2.52 and 5.1. 5.1 rather, 5.1 and 5.3 is what we have got. Let us take one more example where we will consider the random variable x has a mean 0 and variance 1. So mu x is equal to 0 and sigma x square is equal to 1. Then with the transformation 2.60, okay, with the transformation 2.60, which will correspond to y is equal to ax plus b. The mean of y is mu y is equal to a mu x plus b is equal to b. This will be 0. So therefore, we'll have the value equal to b. Similarly, the variance of y is sigma x square is equal to a square. Sigma y square is equal to a square, sigma x square, and this is equal to 1, and therefore we'll get a square. So therefore, with the condition 2.170, the transformation 2.60 becomes y equal to sigma yx plus y. So the random variable x may be transformed to another random variable y with specified mean and variance, with a specified mean and variance, which is mu y and sigma y square. So another application of the linear properties of expectation operator is related to the variance. So we can take the variance, and variance you can write over here, expand this, x square minus 2 mu x plus mu x square, and if you try to simplify this, you'll get expectation of x square linear combination minus 2 into mu x ex, because these are two constants only, and mu x square, this is just a constant, so expectation of that will be mu x square itself. So consolidating this, we'll get mu x square is equal to expectation of x square minus mu x square. So this is mean of the squared value, and this is the square of the mean. Okay, this is mean of the square, and this is square of the mean. If you subtract them, you will get the variance. So then the first and second moments about the version for an arbitrary uniform random variable are shown in 2.51 and 2.52, and if we combine 2.51 and 52 with 2.72, if we what we call join the 2.51 and 2.52 with the 2.72, we are going to get the sigma y square is equal to y2 minus y1 squared by 12, and that is same thing as 2.53 itself. Okay, if you take 5.1 and 5.2, which is there over here, these two, if you take them 5.1 and 5.2, then you'll get an expression which is similar to this whenever we apply the rule which we have just seen. It just corresponds to sigma x square is equal to expectation of x square minus mu square. So if you just substitute in each one of this the value which we have got there, then we'll get the sigma y square is equal to this value. So this is same result as in 2.53, which was obtained earlier with direct integration. Okay. Let us take another example, and that is PDF for the exponential random variable is written like this. So where the red constant lambda is greater than 0, the mean for the exponential random variable is ex, lambda is just a constant, 0 to infinity, x e to the power of minus lambda x dx. And this has to be again solved by the integration by parts. And if you solve this by integration by parts, this will just turn out to be 1 by lambda squared into lambda and then lambda. Then the mean of x square for the exponential random variable is, we can try to write e of x square, that is mean of the square of x square will be lambda integral 0 to infinity x square into 4 of minus lambda. So again, we need to apply the what you call integration by parts. So that will give us 2 by lambda square. Combining 2.73, 74, and 72. 73, 74, and the 72 which we have written over here. Then we will get sigma x square is equal to 1 by lambda square. Okay, sigma x square is equal to 1 by lambda square. So if the random variable is discrete, now till now we considered continuous case where we considered integral only, but now when it is discrete, the what you call we can try to apply it for 2.45 equation with the 2.30 and obtain e of g of x is equal to integral of minus infinity g of x, and we can try to substitute for the fxx value over here. Okay, fxx as the I equal to 1 to n pi del of x minus x I dx. Okay, we are just writing it in terms of the impulse functions, the value for the PDF, or sometimes pi is known as the PMF over here. So pi is just a constant, you can just take it out, and sigma of minus infinity, same thing as this, right? And then sigma is also taken out over here. Integral, we are just trying to exchange the two, what you call summation and integration. So if you try to solve this over here from the signals and systems, this is very clear that this is nothing but g of xi. Okay, so this is convolution integral convolving with the unit impulse function will give us the same value itself. That is what this is giving us at the particular value x equal to xi. At the particular value x equal to xi. So we'll get this itself at x equal to xi because we have here del of x minus xi dx, where the pi are the probability mass function for the discrete random variable. So we can use this over here 2.76 expression for the moments in the 2.46, 2.47 and 2.48. This you can substitute in the expressions for the moments 2.46, 2.47 and 2.48. So we'll get, if you do that, we'll get just this mu x is equal to sigma of xi pi, and e of x square is equal to sigma xi square pi. E of x minus mu x square is equal to sigma of xi minus mu x square of pi. Now we can go for the next, the example for the discrete case. So assume, we can assume the values which we considered earlier, xa equal to 1.1, xb equal to 2.5, and xc equal to 3.4 in the example which we considered in the last class. Then with this value, the mean of the discrete random variable will just turn out to be at 1.1 we have the x equal to 1.1, the corresponding value will just turn out to be we can write this what you call the probability at that point value, because this is nothing but this equation over here xi pi. So xi is 1.1, probability at that time is the PMF value at that time, or probability at that time is 0.24, plus the second value is 2.5, and the probability at that time is 0.32. The third value is 3.4 with the probability equal to 0.44. Then you get 2.56, and this is the mean. So note that in the case of the discrete random variable, the mean is typically not one of the original data values. So that is in this example, mu x is not equal to xa, mu x is not equal to xb, mu x is not equal to xc. Most of the time, it will not be equal to any one of these xa, xb, and xc. So calculations using 2.78 and 79 will give us the e of x square and mu of x square, the sigma x square.
Power
off. We are talking about these two values over here.
Power on. Connected.
So we can again, we only that will get a xa square. Okay, xi square will be for each xa square here, xb square here, xc square here. The probability will remain same because in the formula, the probability is just, without any power. Similarly here, we can try to find out this. Probability is just the same. So you can just write 1.1, this value itself minus the mean whole square into 0.24, 2.5 minus the mean whole square multiplied by 0.32 and so on. So we'll get it as 0.8232 if you simplify this. So thus we'll get this and this value as 7.3768 and 0.8232. So if you we can always find this value by means of using this and this. That is, this squared you'll get in the later term. In the first term, you'll get this 7.3768 minus 2.56 squared will give us again 0.8232, which is same as this. So let us take one more example of what is known as the Bernoulli or binomial application. The event A has the probability P and the event A bar has the probability Q equal to 1 minus 1. So if the event A is specified to be counting random variable, then we have the mean mu x equal to 1 into P plus 0 into Q. Probability of the mean corresponding to the first probability P, which is occurring, and A bar is for A bar is for 0. So therefore Q, right? So 1 into P plus 0 into Q will just give me P. So this is 1 and this is 0. That is what we are considering. Then we will get this. Further, with 2.79, the variance will be 1 minus P whole squared P plus 0 minus P whole squared Q is equal to PQ. So as a check in the result in 2.81, we can calculate this value, which is, this minus of this square. So that is, what you call, we can just try to write that, and expectation of x square will be 1 squared P plus 0 squared Q is equal to P, or otherwise you can just try to write P minus P squared will be the value there, and that will give us P into 1 minus P, that is equal to PQ. So you can find this using this and this, or you can find this using this and this, one and the same. Okay, so you can write over here as, once we know the mu x and the E of x squared, so then we'll get P minus P squared, right? This minus this over here, that will give us the value equal to this equal to PQ. So if you have any doubts, you can ask me, right, till now. Otherwise, in the next session, we will try to solve by hand some of the examples given over here, right? So 29, 32 and all that. So any doubts you have? Temporarily, I'll just stop the share. If you, again, I'll take back to the share. So if you have any doubts, you can ask. No doubts? We'll go into the next session once this stops. Till then, you still have time for asking doubts.